Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Derivation, we'll be continuing our journey in the grade 12 syllabus for physics in CBSE. The chapter that we were dealing with was chapter number 14, Semiconductor Electronics, Materials, Devices, and Simple Circuits. So today we'll be dealing with some more important descriptions and derivations, and we hope you find it interesting. These are very important because they can be asked for a 5-mark question. So the first description is to describe a junction diode as a half-wave rectifier with working diagrams and waveform graphs. So what is a rectifier? So a rectifier, it's basically a device which, in regular terms, converts AC to DC. So this is the device that converts AC to DC current. And there are two types of rectifiers. One is a half-wave rectifier and the other is a full-wave rectifier. So a half-wave rectifier. A half-wave rectifier works on the principle of using one semiconductor diode. The resistance of the PN junction becomes low when it is forward biased and it's high when it is reverse biased. So let's look at the working of a half-wave rectifier. So during the positive half cycle, a diode D becomes forward biased. It conducts the current flows through external resistance RL. Now don't worry, we'll be drawing that diagram just to make it clear. So it conducts and the current flows through the external resistance RL. The output across RL vary in accordance with AC input. During the negative half cycle, the diode is reverse biased. So that means no current flows through, due to which there is no output across RL. So let's look at the diagram of a half-wave rectifier. So basically you have an AC source and then you connect a coil, a current carrying coil, and then the current carrying coil is close enough to another current carrying coil, so they undergo mutual inductance. And then the second coil is connected on one end to a PN junction diode in forward bias, and on the other end is crossed by a section of the earlier wire which has a resistance RL. So this is the diagram of a half-wave rectifier. So as you can see, Here we use only one PN junction diode, so if the polarity changes, then the biasing of the diode becomes reverse, in which there is no flow of current across RL because the diode has infinitely high resistance. Next, let's look at the waveform graphs of a half wave rectifier. So when we're looking at waveform graphs, what you can see is that the input is a pure AC current. AC voltage is the input given to the half wave rectifier. And the top half, the crest, is at Vmax, and the trough is at minus Vmax. So that is the AC input. If you look at the output of the resistance RL, then you can see that for the time that the voltage is above 0, the current is flowing through the circuit. But then during the reverse polarity, the current is in reverse bias, and so therefore there is no formation of current. Then at the next crest, at the next positive value, the current starts appearing again. So now you can see that there is no current when the diode is in reverse bias. So the crests show Vmax, while the bottom part of this graph shows 0 voltage and therefore 0 current. So therefore, in a half wave rectifier, there is pulsating AC current passed through the resistance. So this type of rectifier isn't of much use, and that's why we have started using a full wave rectifier. So now the next question is to briefly describe a full wave rectifier, a junction diode acting as a full wave rectifier with workings, diagrams, and waveform graphs. So a full wave rectifier has a slight difference from a half wave rectifier, and that is evident in the number of diodes present. So let's look at the working. So in a full wave rectifier, the main difference is that instead of one diode, you now have two diodes, and therefore the problem gets interesting. So during positive half cycle of input AC voltage, upper end A of coil is at positive potential with respect to center tap, and the lower end which is B of the coil is at negative potential. The diode D1 is forward biased, and the diode D2 will be reverse biased. So there will be infinite resistance with respect to D2, but there will be conduction of current through D1. So therefore, since you have a center tap in the coil, therefore current does flow through the circuit. So D1 conducts and D2 does not. Current flows through RL, that is the resistance. Now, during negative half cycle, what happens is that the end B is at higher potential with respect to the end A. So in this scenario, D2 is forward biased due to the reverse polarity, and D1 is reverse biased. And that is the main difference out here with respect to the working. D2 conducts current and D1 does not. So the good thing about a full wave rectifier is that current flows through RL at all times. So therefore, the rectifier is called as a full wave rectifier, because for a full wave of the AC input, there is an output. So now let's look at the diagram of a full wave rectifier. So basically, you have an AC source again, which is connected to a current carrying coil that produces magnetic field. And this coil is now under mutual induction with a second coil, which is connected to a different circuit. Now this circuit has its differences. On one part, which is A, a diode named D1 is connected to the circuit. And at the other part, say B, a diode D2 is connected to the circuit. Now, both of these are connected to the resistance RL, and we have a voltage V output as well. So another interesting bit is that the lower arm is earthed as well, and the earthed bit is connected on the other hand to the center of the coil, and this part is known as the center tap. So basically, the center of the coil is earthed, which means that there is the earthing of the coil, so it makes the potential here 0, and it also makes the potential across on one side of the resistance as 0. So through the other side, you can have current flowing through both D1 and D2, which means that there is an output. So this is how a full wave rectifier converts AC current to DC current. So how would you represent the waveform of the input and output? Now for this, let's consider this diagram, which is an integrated diagram of both the input and the output. So as you can see here, when you take input, the input graph will look like the graph of an AC voltage source. Okay, so this is how the AC input looks like. Now in the positive cycle, the diode D1 is conducting current, but the diode D2 does not. So now we have the crests of the graph getting registered as the output, but the troughs of the graph are not getting registered. If you look at the negative cycle, in the negative cycle, the diode D2 is connected in opposite polarity. However, it's still forward biased. So that means now you still get positive values for the negative potential. So now what happens is that once you check the output, you can see a constant current, or I can say constant positive value of the current, mostly, which is flowing through the circuit. So if you look at the output, you can see that there is the presence of a vibratory, a pulsating DC current. So the output here is DC current, and this is the kind of current that we use in order to power our machines, because our machines have semiconductors and they need DC power. So that's how you use a diode as a full wave as well as a half wave rectifier. Now the last part of this, the last question, is to briefly describe an LED with its construction, working, and a diagram. An LED is basically a semiconductor light source that emits light when current flows through it. It's a specialized p-n junction diode with similar electrical characteristics to that of normal diodes. So now let's look at construction. So when we're talking about construction, we need to know that LEDs are made from a very thin layer of fairly heavily doped semiconductor material. Depending on the amount of doping and material used, an LED will emit a colored light in forward bias at a particular wavelength. So the construction is to deposit 3 semiconductor layers on the substrate. So in particular order, it will be n-type semiconductor, followed by an active region, and then by a p-type semiconductor. So all 3 of these will be the parts of an LED, and the active region plays a very important role in an LED. So if you look here, you find that the n-type is at the bottom, the active region is sandwiched between the n-type and the p-type, and the p-type comes on top. And the active region is the region which gives you photons. The n-type is filled with electrons, and the p-type is mostly filled with holes. Those are positive equivalents of electrons. So this is the construction of an LED. What about the working of an LED? So when LED is forward biased, free electrons from n-type and free holes from p-type semiconductor are pushed to the active region. And in this active region, free electrons and holes recombine so that means the holes and the electrons get together and an invisible or visible light is formed. Most of the light is emitted by the recombination of most of the charge carriers at the active region, which is also known as the depletion region for an LED. So this is the general working of an LED. Now let's look at the diagram for an LED. So most of us would have seen the LED outside with the epoxy tube, but if you look at inside, then there is a whole lot to it than what meets the eye. So first of all, you have the anode here, and these anodes and cathodes have a specific shape because of their function. And now let's look at the cathode. The cathode is right here. And on top of the cathode, you have a couple of things. This right here is a reflection cavity, and we have an LED chip on top of it. And this LED chip is connected to the anode by a bonding wire. And then the whole structure is covered by the epoxy tube, the epoxy lens that you see outside. So let's erase a bit so that our diagram looks a lot neater. So yeah. Okay, let's draw the epoxy again. This is the epoxy lens, and you can draw a round head at the bottom to finish off the diagram. So this right here is the epoxy lens. This is the cathode, which is negatively charged. And this here is the anode with positive charge. And this piece of equipment right here is what is known as the reflective cavity. The reflective cavity is surmounted by an LED chip from where the light is incident. And finally, the wire that connects the anode and the cathode is known as the bond wire. So this is the diagram of an LED. This is the simplified version of it, but it contains all the essentials. So that concludes this episode of Derivations. We hope you found this chapter interesting. Semiconductor diodes are a pretty important part of the syllabus for grade 12 CBSE. So we hope you found this video informative and useful. For more of our useful and interesting content, don't forget to subscribe to our channel, which is Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.